So problem number 7, we're talking about Jackson is in charge of creating the work schedule for employees at Big Waves Water Park. If too many employees are scheduled, the water park loses money. On the other hand, if too few employees are scheduled on a busy day, customers are unhappy and the water park could lose business. Jackson knows there's a relationship between daily temperature and the number of customers, which in turn determines the number of employees needed. So there's this relationship between daily temperature and number of customers, and that determines the number of employees needed. So basically, number of customers determines the number of employees, but daily temperature determines number of customers. So we can go ahead and assume daily temperature is going to determine the number of employees. So he took this data, he collected data around the temperature, forecast and the number of employees that were needed that day. And the first thing they want us to do is to graph this data. So I'm going to, again, we need to choose a scale. We've got temperature is the independent variable, and that's in Fahrenheit. And employees, the number of employees is the dependent variable. So we're putting the temperature down here on the X, number of employees on the Y. And we need to get all the way up to 90 on temperature. And we need to get from 15 to 40 on employees. So again, we only need the first quadrant because it's all positive numbers. And there's no reason to make a jump in the graph because we can get up to 90 just by counting from 0 to by tens. So I think 10, 20, 30, 40, 50, 60. So that wouldn't, but if we did this, 10, 20, 30, 40, that'd be 60, that'd be 80. So we could easily get in 90 right there. So, and then notice I started here as 0. So 0 counts as what you're counting from. 0, 10, 20, 30, 40. Same thing going up. We need to get up to 40. So we could probably go, this is 10, right? So from 0 to 10 is 2 blocks. And from 10 to 20 would be 2 blocks. 10 to 20 to 30, 30 to 40. So just make sure you count from 0 unless you put a break in the graph. So 2 blocks is 10, 2 blocks is 10, 2 blocks is 10. All right, now I need to graph the data. So go over to 65 and up to 15, over to 70 and up to 19, 75 and up to 27, 80 and up to 31, 85 and up to 36, and 85 up to 36, and 90 up to 40. Now I will say that now that I'm looking at the really scrunched up data, we may have wanted to put a break in the graph and started over here at 60 so that we could spread this out and looked at it a little bit more spread out instead of scrunched up. But this is still accurate enough that we can see a trend of a line, right? And now we need to find an equation for the line of best fit. Now, some of you know how to put this data in your calculator and get the calculator to do it. Others of us, we just looking for a general rate of change, right? So if we kind of look here and put a line through these points, it looks to me like in general, if I choose this point and maybe this point, it would give me a decent line of best fit. So if I choose this point and this point, I could figure out a decent slope for that. So from here to here, I am increasing. So remember, a line of best fit, this is just like all the other cases. What we're seeking, when it says find an equation of a line of best fit, we're seeking slope and y-intercept. So I'm talking about choosing this point and this point, my first point and my last point, and using those to help me write an equation of a line of best fit. So seeking the slope just means rise over run. So I've increased by 25. So this is plus 25 here. And I've increased here by 25. So that actually gives me a slope of 1, which is pretty nice to work with. If you notice here, if I had chosen these 2 points, it would have gone a little bit this way, but the slope would have been 5 over 4, which is bigger than, it would have been 4 over 5. Yeah, this is the rise. I had this backwards looking at the table. So this is the rise. So 4 over 5. It would have been 4 over 5, which is just a little under 1, right? So notice you're not going to get an exact steady rate of change here when it's actual real life data, but you are going to get an overall linear pattern. So you have to estimate the best one. So this isn't perfectly linear data, but it generally goes in a linear fashion. So I'm going to go with my slope is 1. And then I'm going to use one of these points to help me find the y-intercept. So again, I can just do the y equals mx plus b. I know that when my slope is going to be 1, and when my x is 90, my y is going to be 40. So I can use that information to help me find a b. So 40 equals 90 plus b, subtract 90. So b equals negative 50. So in general, my line of best fit is y equals 1x plus negative 50. Now, if you did this and chose other points, you might have gotten something slightly different. It shouldn't be extremely different from this, but you might have gotten that slope of 4/5, anywhere between 4/5 and anywhere between 0.75 and 1.25 for a slope would probably be okay. And then your y-intercept would vary a little bit depending. Now they want us to predict the number of employees needed when the temperature is 77. So we have to use this equation. So again, if your equation's different, you might come up with a different number slightly, but the prediction should be somewhat the same. And the idea is the same. So I'm going to predict the number of employees needed when the temperature is 77. So that's my x value. So I'm going to plug 77 in here. And y equals 77 plus negative 50. So that's just 77 minus 50, which is 27. So the prediction is 27 employees when it's at 77 degrees. And if you look here, that's fairly reasonable. It's not going to be that different from the temperature of 75. So we'll go ahead and that's what my model predicts. Now, I'm not going to do D and E because I already did that back here in problem number 5. So if you need help interpreting slope and y-intercept, you're going to need to go back and watch number 5 and then interpret slope and y-intercept in the context of this problem this time. But F I will go ahead and talk about. On a day when the temperature is 85 degrees, there are approximately 550 customers at the park. And use this information to predict the number of customers on a 97-degree day. So what do we imagine? I imagine that there's a proportional relationship between customers and employees, right? So I am going to go ahead and guess that I'm going to go ahead and say, well, 85 degrees, on an 85-degree day, I'm going to need about 35 employees. Right? And so on a 97-degree day, how many employees am I going to need? I'm going to need 47 employees. So I know how to predict that, right? So I've got this information. But now I've got this other relationship, the one between employees and customers. And I'm going to assume that's a proportional relationship. Like you need a certain amount of employees for every amount of customers. So on 35 employees, for 550 customers, you need 35 employees. So then if you have 47 employees, how many customers do you have? And so this is kind of combining the information. I'm using my model to predict how many employees given a certain temperature, and then I'm using proportional thinking to set up this proportion that I can then solve to get the number of customers, to guess how many customers I'm going to have on a 97-degree day. So I'm going to leave that there for you to finish solving, but that's how I would set that up to make that prediction.